This video is going to remind you how the integral test creates bounds for any estimate that you do. So let's say you were finding a sum to infinity and you estimated it just by summing the first 5 terms. You can figure out what the upper bound and the lower bound of the estimations are for your approximation. Okay, and this is it. Okay, so this is something you need to remember from your formula sheet or understand. Okay, so I'm going to remind you, I'm going to do it exactly like we did in class, where these upper and lower bounds came from. Okay, so for an integral test, we know we have a positive continuous decreasing function, so I've drawn this. Okay, so when we look at this, what I want to do is show you how these rectangles are actually representing your infinite sum. Okay, so if you think about each of these rectangles, this has a width of 1, every single one of them. Okay, even from k minus 1 to k, that's a width of 1. If you look at how tall these are all done on the right-hand endpoint. So this first one is f of 1 tall. That's how tall it is. So f of 1, that's the height at the right-hand point, times 1, the area of this is f of 1. Okay, and similarly, this is f of 2 high, this is f of 2, this is f of 3. Okay, now it's going to keep going, but let's see kind of what happens here. So here, this one, and it's not drawn in, but if I continue the same pattern there, okay, this would be f of k high times 1. This one, going with the right-hand endpoint, f of k plus 1, f of k plus 2, and so on. Okay, and so what we're going to look at doing is trying to figure out bounds for the infinite sum. So if you think of this sum, be putting in 1, 2, 3, 4, 5. This would be the same as adding up the area of all these rectangles. So f of 1 plus f of 2 plus f of 3 infinitely. Okay, forever and ever. Now you can split this at any point that you want to. So what we're going to do is we're going to add up first from 1 to k. Okay, so that would be adding up all of these. Okay, so this would represent the summation from n equals 1 to k of f of n. Okay, because we're going f of 1 all the way up to f of k. And then we can split and do the rest of them. Okay, so let's grab another color here. F of k plus 1 to infinity. Okay, so this would be the summation of n equals k plus 1 to infinity. Just keep going all the way out here. Okay, and of f of n. So basically, even though we're going to sum from 1 to infinity, I'm going to split it. We're going to add up from 1 to k, which will be these, and then from k plus 1 to infinity. Okay, now we're going to leave this part alone. Okay, that's a finite sum, and we're actually going to calculate it. And what happens is, if we just integrate it here, we can notice that for this particular situation, it is above the curve, is above the rectangles. Okay, the curve is above the rectangles. So if I was to take the integral of this, that would be larger than the rest of what I need. Okay, so this part is larger. So the integral is larger than the sum of the rectangles. Okay, and so we now just have this as our upper bound. Okay, we know that it's going to be, when we do this, it won't be greater than this. Okay, when we find this infinite sum, we now have a nice upper bound. Okay, so if I just sum the first 20 terms and I want to know an upper bound for it, I would just have my sum for the first 20 terms plus the integral from, oh, it looks like I need to fix that. It needs to, okay, and actually we had a brief interruption there, someone coming in the room, but we don't need to fix anything at all. If we look here from k plus 1 on, we notice that the upper bound there actually is from k to infinity there. So we have that right, and we now have developed an upper bound. Okay, so it turns out in this case we're creating a bound for the rectangles, which is the integral. Okay, and so now we want to do the same thing, only with a lower bound. So if you notice the way this is created, the integral is actually a lower bound here. So let's look at how that is different. So if you notice the rectangles are created differently, they're all created here on the left-hand side, and all the rectangles are above all the way through. Okay, so when we look, we're still going to have widths of 1. If we look at how high this is f of 1. So we've basically just scooted everything over a little bit. This is 1, and we have f of 2. And then if we look at this one, which we don't have in, but if we're doing the rectangles being above, then this would be f of k minus 1. And then this little guy would be f of k. This one would be f of k plus 1. I think it's a little hard to read there, but this one would be f of k plus 2, and so on. So we're doing the same idea here, that my rectangles are representing my infinite sum. Okay, putting 1, putting 2, so it's a sum from 1 to infinity. Now I'm going to do the same thing and divide it up, okay, and we're going to add up f of 1 through f of k, which is going to go to here. Okay, so that's this part. Okay, so that's f of 1 to f of k. Let's see if I can find the pink one here. And then we can go from f of k plus 1 on. Okay, so that would be this part. So again, we're just doing a little bit of a split. Okay, so now if we look though, we can see that the integral is smaller than the rectangles. Okay, so either way you want to look at it, but the integral, and we're going from here on, in this case, is from k plus 1 to infinity. Okay, and we can see that that's smaller than the sum that we're representing here, and that sum of the rectangles is this. And this is the sum of the rectangles. Okay, and so in this case here again, we're seeing that the integral is smaller. So you see we've got the integral that we've replaced it with is smaller than the rectangles, or the rectangles are larger than the integral that you have here. So what that does is that creates for us a lower bound. So when you put this all together, okay, you see that your sum, your infinite sum, can be bound by, here's our upper bound from 1 to k, and then from add on the integral from k to infinity. Okay, so this is our upper bound. This is our infinite sum, and this is our lower bound. And this is actually here. Okay, notice they did s sub n for the sum. Okay, plus, and they have n plus 1 to infinity. That's the same as our k plus 1 to infinity for the lower bound, and there's our upper bound. Okay, so you have this information here on your study sheet. So just to show you how that can be used, okay, it says find an upper and lower bound for this sum, and you're finding the estimate for the bounds using the first 5 terms, because they'd be different depending on how many terms you use to estimate it. Okay, and so what we're going to do is we have the sum from 1 to infinity. That's what we want to find. And we're going to create an upper and a lower bound. So our estimate is just the summation from 1 to 5, because we're going to use the first 5 terms to estimate it. Okay. Now you can put that in one at a time, but you can also just do that on the calculator. So we'll just do that real quickly. And so we have summation, and we're doing n equals 1 to 5, and our function was 1 over n squared. Okay, I'm kind of in the mood here for a decimal. So I've got, we'll just write that down, 1.4, I'm going to go 1.464. Okay, and so that's our estimate, and I want to create an upper and a lower bound for the infinite sum of this. And so I just need to squeeze that. Actually, let's just put that over here, because that was our, okay, that was our estimate. And it's going to be between that plus something and that minus something is essentially what we're looking at. So if you look at your upper bound, you're estimating it with 5, and so then your integral is going to be from 5 to infinity of 1 over x squared. Okay, and that's going to be what creates your upper bound. It's bound by that integral. So then we know to change that to be the limit as b approaches infinity of the integral from 5 to b of x to the negative 2 dx. So this would be the limit as b approaches infinity. Just a nice little power rule. Add 1 to the exponent times the reciprocal. And we're going to evaluate that from 5 to b. So we have the limit as b approaches infinity. Let's just write this as negative 1 over x from 5 to b. So this would be the limit as b approaches infinity of negative 1 over b minus negative 1 over 5. And so as b goes to infinity, this term is going to go to 0. So you just have 0 plus 1/5. And so your upper bound there is 1.464 plus 1/5, or about 1.664. Okay, and so that is our upper bound for this infinite sum. And what we're going to do is just similarly, we're going to find the bound for the lower bound. Okay, so here we're going to do the summation from n equals 1 to 5 of 1 over n squared plus the integral from 6. And you think about it, this is going to be a smaller area here, kind of one way to try to remember the lower bound being the plus 1. Okay, so we're really narrowing it pretty tight. Now, this part we already know is 1.464, and we can, because we're clever like that, if this was 1/5, and we're just doing essentially the same thing from 6 to infinity, so this is just going to turn out to be 1/6. You can work it all out, and so that just becomes 1.630. So that kind of shows you how you can narrow down your infinite sum pretty well for a positive finite decreasing sequence.